Distinguishing scalars and vectors. Welcome, everyone. Today, we are going to begin a fundamental topic that serves as the building block for both physics and advanced mathematics. As we study the universe, we constantly encounter various physical quantities, things like how much an object weighs, how fast a car is moving, or how much force is being applied to a surface. However, to analyze these quantities accurately and perform precise calculations, we cannot simply treat all measurements the same way. We first need to categorize them based on the specific type of information required to describe them completely. Some measurements are simple, while others require more detail to be meaningful. To make this distinction clear, we divide these quantities into two essential categories: scalars and vectors. Over the next few slides, we will explore exactly what makes each one unique and how to tell them apart. Scalar quantities. So, what exactly is a scalar? Simply put, a scalar quantity is a physical measure that is fully described just by its magnitude, which is just a fancy word for its numerical value and its unit. The most important thing to remember here is that a scalar does not possess a direction. Let's look at the specific characteristics that define scalars. First, they are represented by a single number. Second, they follow the ordinary laws of algebra that you are already used to. For example, if you take 2 kilograms and add 3 kilograms, you get 5 kilograms. It's straightforward addition. Finally, a key feature of scalars is that changing the orientation of the observer does not change the value. If you turn around, the mass of an object doesn't suddenly change direction or value. To make this concrete, let's look at some real-world examples. First, think about time. If I tell you that a lecture lasts for 45 minutes, that information is complete. You don't need to ask 45 minutes towards the north, because time doesn't have a direction. Next, consider mass. If an object has a mass of 5 kilograms, that description is finished. Mass is purely a scalar. It doesn't point anywhere. Then there is temperature. If I say the room temperature is 25 degrees Celsius, you understand the state of the room perfectly without needing any directional component. Lastly, let's look at distance. If you walk 100 meters, you have described the total path length you traveled. While we will soon learn about a more complex version of this called displacement, the distance itself is a scalar because it only focuses on the total ground covered, not the direction. Now that we've introduced the idea that physical quantities are categorized into two main groups, let's dive into the first group, scalar quantities. Now that we have a clear grasp of scalars, let's move on to the next slide to see how vector quantities differ by adding that crucial element of direction. Vector quantities. Unlike the scalars we just covered, a vector quantity is a physical measure that requires both a magnitude, that is, a numerical value, and a specific direction to provide a complete description. Without that direction, the information is simply incomplete. Let's look at the specific characteristics that define a vector. First, they are represented by both a numerical value, which we call the magnitude, and a direction. Second, it is very important to note that vectors do not follow the ordinary laws of algebra that we use for scalars. Instead, they follow a specialized set of rules known as vector algebra. This is something we will dive deeper into later in the course. Finally, if you were to draw a vector geometrically, we typically represent it using a directed line segment, which looks like an arrow, where the length represents the magnitude and the tip of the arrow points in the specific direction. To make this more concrete, let's look at some real-world examples. First, consider force. Imagine you are applying a force of 10 newtons to a door. The outcome of your action depends entirely on direction. The result is very different if you push the door inward versus pulling it outward. Next, we have displacement. Now, be careful here, as we will compare this to distance in a moment. While distance is a scalar, displacement is a vector. It represents the shortest straight line distance from your starting point to your final position. For instance, saying you moved 5 kilometers east provides both the magnitude and the direction. Lastly, there is velocity. You might be familiar with the term speed from our previous slide, but velocity is different. Velocity is the rate of change of displacement. It doesn't just tell us how fast an object is moving, but also the specific direction in which it is traveling. Now that we have a clear understanding of scalars, which, as we just discussed, only require a magnitude, let's turn our attention to the second category, vector quantities. In the next slide, we are going to perform a comparative analysis to see exactly how these two concepts, like speed and velocity, differ in a practical scenario. Comparative analysis, a step-by-step example. Now that we have defined what scalars and vectors are in the previous slides, let's put that theory into practice with a comparative analysis. To make the difference crystal clear, we are going to compare two very similar sounding terms: speed, which is a scalar, and velocity, which is a vector. Imagine this scenario. You are sitting in a car that is traveling along a perfectly straight highway. First, let's look at step 1, where we describe the speed. Suppose you glance down at the car's speedometer. The needle points exactly to 60 kilometers per hour. At this moment, we have a scalar quantity. Why? Because the speedometer only tells us how fast the car is moving. The information is complete as it is. We don't need to know which way the car is facing to understand its speed. Now, let's move to step 2, where we describe the velocity. This time, instead of just looking at the speedometer, let's also check a compass. We see the car is moving at 60 kilometers per hour, but we also see it is heading towards the north. Here is our conclusion. This is a vector quantity. Unlike speed, the description of velocity is incomplete if we only mention the magnitude of 60 kilometers per hour. To truly describe the velocity, we must include that directional component, north. As we will see in our summary table in the next slide, this addition of direction is exactly what transforms a simple scalar into a vector. Key takeaways. Now that we have explored the individual definitions and real-world examples of both scalars and vectors, let's bring everything together. I have prepared this summary table to help you compare them side by side, which will be very useful for your revision. First, let's look at the requirement row. As we discussed in the previous slides, the fundamental difference lies in what information is needed. For a scalar quantity, you only need the magnitude, that is, the numerical value and the unit. However, for a vector quantity, the magnitude alone isn't enough. You must also specify a direction to have a complete description. Next, let's consider how these quantities change. A scalar quantity is quite simple. It only changes if its magnitude changes. But be careful with vectors. A vector quantity is more sensitive. It can change if the magnitude changes, or if the direction changes, or even if both change simultaneously. Even a change in orientation alone makes it a different vector. Moving on to algebra. This is a crucial point for your upcoming problem-solving sessions. Scalars follow the ordinary laws of algebra that you are already familiar with, like simple addition and subtraction. But as we touched upon in slide 3, vectors do not follow these simple rules. Instead, they follow the rules of vector algebra, where we must account for the angles and directions between the quantities. Finally, let's review the examples to solidify your understanding. For scalars, remember our earlier examples: time, mass, temperature, and speed. For vectors, we have force, displacement, velocity, and acceleration. Keep this table in mind, because in our next slide, I am going to highlight some common pitfalls where students often get tripped up when applying these differences in exam questions. Common mistakes to avoid. First, please be careful not to confuse distance with displacement. I often see students using these terms interchangeably, but as we discussed in our comparative analysis earlier, they are fundamentally different. Remember, distance is a scalar. It simply tracks the total path you have traveled, regardless of direction. Displacement, however, is a vector. It represents the straight line distance from your starting point to your ending point, and it must include a specific direction to be complete. Second, don't assume that a negative sign always means opposite direction. This is a tricky one. When we deal with scalars, like the temperature example we saw on slide 2, a negative sign usually just indicates a value below a 0 point. For instance, negative 10 degrees Celsius simply means it is cold. But when we are working with vectors, A negative sign, such as negative a, has a very specific geometric meaning. It indicates that the vector is acting in the exact opposite direction of the original vector, a. Finally, and perhaps most importantly, never ignore direction when solving vector problems. A very common error is to simply add the magnitudes together as if they were scalars. For example, if you have a force of 5 newtons acting east and another force of 5 newtons acting west, you cannot simply say the total force is 10 newtons. Because these are vectors acting in opposite directions, they actually cancel each other out, resulting in a resultant force of 0 newtons. Always consider the direction before you begin your calculations. Now, before we wrap up today's lesson, I want to touch on some common pitfalls. As we've seen throughout these slides, the distinction between scalars and vectors is subtle but incredibly important. To ensure you don't lose marks in your exams, let's look at 3 common mistakes to avoid. With that, we have covered the essential differences between scalars and vectors. Keep these distinctions in mind, and you'll be well on your way to mastering this topic.